We have covered all kinds of things. We looked at electrostatic force, the Coulomb force. We looked at electric fields. We looked at potential energy. And then we looked at just electric potential. And each one got its own letter. F, E, P, E, and V. And each one had its own things going on. So over here to the left of this, I've got two vector quantities. Over here to the right of this, I've got two scalar quantities. And I want to kind of combine these a little bit. My force equation, that looked like a Q over R squared. Electric field, that was a KQ over R squared. Potential energy, KQ over R. Electric potential, KQ over R. There is a lot of similarity between these, and so I'd like to write a quick table to kind of pull them together. I'm going to have a location only term, and then I'm going to have an object specific quantity. Then we'll do scalars, and we'll do vectors. Because sometimes tables are an easy way to think through things or keep them organized. So when we do this, I like to look at it this way. My location only quantities, my location only scalar quantity, this is my electric potential, and it is KQ over R. My object specific version of this is my potential energy, and that is going to be KQ over R multiplied by the charge of my object. My location only vector, that's the electric field, and that is KQ over R squared to find the magnitude. And the magnitude of my force, which is the object specific vector, is going to be KQ over R squared multiplied by the charge of my object, which means if I am moving from the top to the bottom, all I have to do to get there is multiply by the charge of my object. I also have a nice way of looking at the scalar versus vector part of this. To get from these scalars to these vectors, all I'm really doing, I've got an R on the bottom, I've got an R squared over here, so to go from a scalar to a vector, I am effectively dividing by R. Or from the vector to the scalar, I'm multiplying by R. So I have a good way of moving from one side of this table to another. This means I can come up with some equations that relate these really easily, right? My potential energy is equal to Q times my electric potential, or my potential energy is equal to Q times my electric potential, which maybe I've got from an electric field vector. So E times R gets me from E to V and then down to potential energy. So I can write an equation this way. I might say a force is going to be Q times E, and that one's really helpful. Those are both vector quantities. I can actually throw the vector signs back on there. Maybe I'd like to know the electric field between two parallel plates, so maybe I've got a plate here that's sitting at a potential of positive 20 volts joules per coulomb, and I've got another plate here, I'm looking ahead just a little bit, and I've got another plate here that's sitting at negative 20 joules per coulomb. Maybe those are separated by a distance of 10 centimeters. I can say that my electric field, which I can get from potential difference, right? Potential difference is kq over r. This is kq over r squared. To go left to right, I am dividing by r. My electric field strength is going to be the difference in the potential divided by the separation distance. So in this case, it's going to be 40 joules per coulomb divided by 10 centimeters is going to be 400 newtons per meter. Joule per meter is a newton, so meters. So a newton per coulomb.